Hello, these are the solutions to a review activity over chapters 1 through 9. The first question here is how many atoms are in a 4.0 times 10 to the minus 5 gram sample of aluminum? So all the atoms are going to be aluminum atoms, so we're going to calculate the number of Al atoms. And we'll start with the 4.0 times 10 to the minus 5 grams. We'll use the conversion factor for the molar mass of aluminum. So 1 mole of aluminum is comprised of 26.98 grams. Let's call it 27.0 grams from the periodic table. 1 mole of aluminum is comprised of 6.022 times 10 to the 23 aluminum atoms. So that should work out to 4 times 10 to the minus 5 divided by 27 times Avogadro's number. And I get 8.92 times 10 to the 17. Number 2, how many moles of sulfate ions are in 100 milliliters of a 0.02 molar solution? For paying attention to sig figs, imagine this is 100 mils with 3 sig figs. So how many moles of sulfate ions are in this solution? Okay, let's do it this way. Let's try to see if we can use dimensional analysis, number of moles of sulfate. I'm going to take my 0.00200, just 1 0. Now, this is mole of this per liter. So that's moles of Fe2SO4 per liter of the solution. And then we have 100 milliliters. Let's just do 3 zeros. So just expressing this in liters. So our volume cancels. Fe2SO4 in solution is really, because it's a water-soluble ionic compound, not one of the exceptions for sulfate, this goes to 2 iron, 3 plus cations, and then 3 SO4 minus ions. So we get these ions in solution, not really the ionic compound. And so then we can recognize for every 1 mole of Fe2SO4 we get 3 moles of sulfate into the solution. So we can kind of start the calculation with 0.02 or 0.002 times 0.1. So we have 2 times 10 to the minus 4 moles of iron sulfate, and then times 3 sulfate ions, so it's 6 times 10 to the minus 4. So this is the moles of the sulfate ion in this solution. Question 3, how many moles of water are produced by this reaction of 14.4 grams by the complete combustion reaction? This means we have ample O2 for this reaction. So the number of moles of water, I almost wrote grams, but the question is asking for moles. Number of moles of water would be equal to 14.4 grams of C5H12. I'm going to need the molar mass, so that's 12.01 times 5 plus 1.008 times 12, so that's 72.15. And then from here, we'll use our conversion factor. For every 1 mole of C5H12 that reacts, we form 6 moles of water, and then we're good to go. We could convert to grams, but it's not asking for grams. And so 14.4 divided by 72.15 times 6 is 1.20 moles of water. 30 mils of 0.1 molar calcium nitrate, 15 mils of 0.2 molar sodium phosphate are mixed. After the reaction is complete, which ions have the lowest concentration? Okay, so I got ionic compound. So we're thinking that we have a metathesis reaction taking place or an exchange reaction, so calcium nitrate. If I can remember how to write, would be great. NO3 AQ plus Na3PO4, water soluble. So we're just swapping our ions out. So we're going to form calcium phosphate. PO4 is a 3 minus, a 2 plus, so this should be the formula. And then this is insoluble, so this is the precipitate. From our solubility chart, we could check it, but calcium phosphate's insoluble. Then our byproduct is going to be sodium nitrate. And then this is water soluble. And then our balancing, we're going to need a 2 here to get our 2 phosphates. And then that's going to, let's see, what else do we need? And so that's going to be 6 NaNO3s, and we need then 3 calcium nitrates. It gives us the 3 calciums on both sides, and then the 6 nitrates. Okay, so balance reaction. But what we need to think about is that calcium and phosphate could be going to 0. One of them is going to 0, and then one of them could be left over as an excess reactant. And so there's a few different ways I can think through the math here. I don't hate the BCA chart. I know some of you guys do, but that's fine. But the reason why I like our thought process can come out with the BCA chart, maybe we can do this without even writing out the chart perhaps, but let's think about the chart for a minute, because what I'm thinking is 0.03 liters times 0.1 is 0.003 moles of this, and then my sodium nitrate is 0.015 times 0.2, so that's the same number of moles. And then, but we need more of the calcium nitrate. For every mole of sodium phosphate that's consumed, we need 3 times as much calcium nitrate. So in other words, phosphate can't go to 0 here because this is part of the excess reactant. And so we can see it's the excess reactant, so our change here should go like this. And the X is just, for every X we lose 3X of calcium nitrate for 2X of sodium phosphate, and then we don't really need to worry about this for the sake of this problem, but plus X and 6X for 1 calcium phosphate and 6 NaNO3s. And then if after the reaction, this is the one that's consumed, that can let us solve for X. So if 0.003 minus 3X goes to 0, then we can solve for X as being 0.001. And so then 2 times 0.1001, so we can plug X in here, and then see that we get 0.0010 moles of the sodium phosphate left over. I kind of hate that I'm screwing the sig figs up here, but these should have just been this. So let's try to be somewhat consistent with sig figs and not have that blur our picture here. So 0.0030 minus 3x equals 0. And then allows us to solve for x. We can plug x in and then solve for the remaining amount of sodium phosphate. Now, sodium and nitrate can't be the answer because they're AQ in the product too. So they're never going to 0. The only ones that could possibly go to 0 are the 2 ions that are precipitated, but then the phosphate is present in excess, so it's still in solution, and then the calcium is the one that goes to 0. So all the calcium is precipitated, none of our calcium nitrate is left, calcium is fully in the product that's a solid, and so none of it's left over in solution. And so the phosphate ion remains, but then all of the sodium and nitrate that were initially present remain in the solution as well. Okay, so how could you think about this problem without a BCA chart? Well, that might be just to think about how you have a reaction taking place, which you should write. I mean, I don't think there's any way to avoid writing out this reaction, or at least I would think reaction taking place. I better write it and balance it. And then second to that would be thinking, well, one of the two ions that are precipitated has to remain in excess, and somehow I got to solve the limiting versus excess reactant problem. And so we could calculate how much we need of one given the other, and then see how much we have available of the other. If you can solve that without a BCA chart, that's great, and there's nothing wrong with doing that. BCA chart, I don't know, it takes a couple seconds. And to me, it just really kind of keeps track of almost making it hard to get this wrong. Because, like, imagine we said, well, what if we said that sodium phosphate goes to 0? Well, what would X be equal to? 0.015. Well, then go plug X in over here, and then you're going to have a negative quantity of calcium nitrate left over. So, BCA charts are a tool. We can use them to solve problems and help us understand some of these problems. Question 6. We have a mole of methane produces CO2 and water releases 802 kJ per mole. When 3 moles of oxygen reacts with the stoichiometric quantity of methane, what is the delta H for the reaction? Okay, so for 1 mole of CH4, that's telling us when CH4 reacts with O2 to produce CO2 and water, that this is reacting 1 CH4. This is going to have to be producing 2 waters. Give me my 2 times 4 for 4 hydrogens on both sides. And that's 2 O2 molecules. So that gives me 4 O atoms. And that gives me 2 plus 2 for 4 O atoms over here as well. So we're balanced here, CH4 with 2 oxygens. And so CH4 releases 802 kJs when 1 mole reacts. But when 3 moles of oxygen reacts with the stoichiometric quantities, that would look like this were 3O2, then we're multiplying all of these coefficients by 1.5. So we'd have 1.5 CH4, and then we'd be producing 1.5 CO2, and then 3 H2O. We're still in balance, 6. And then fractional, weird. Or not fractional, it's 3 plus 3, so that's still 6. And then 1.5 carbons on both sides. It's only like 1.5 carbon atoms seems strange, but if you picture having 1.5 moles of carbon, it might make more sense. But if you knew your delta H here was minus 802, then your delta H here is going to be minus 802 times 3 halves, since we multiplied all the coefficients by 3 halves. And so the delta H for this reaction, the release is the minus, and then 3 halves is what we need to multiply it by for being 3 moles reacting. So kind of a strange question. It's really just saying from this reaction, being able to write it out, knowing that its delta H is minus 802, and then we know the other reaction is going to be minus 12, 1.20 times 10 to the minus 3, negative this one here. When was the final temperature when 20 grams of water at 80 degrees C is mixed with 30 grams of water at 20 degrees C? So this is Q of our water that's hot. We're losing heat here. And then we're gaining the heat in our cold water, and it's going this way. So we just need this minus sign up front. So water's losing heat, the cold water's gaining heat. We have our MCS delta T equal our negative MCS delta T, but this is just for we can have one side be the hot, the other side be the cold, and it doesn't matter. Like math is still math. Like you could put the minus sign here, and it's still mathematically the same. And then so we just need to plug the mass and the delta T and the CS on water for one side. Okay. So, and then also we have water for both substances, so the CS cancels. And so we're going to have 20 grams of water, and then our delta T's are T final minus 80 degrees, and then equal to 30 grams of water. And then our TF minus our initial temperature, 20.0 degrees. Okay, and so we just have a somewhat, make that font so weird. Okay, so all we need to do here is do some math. So 20.0 TF minus 1600 equals 30 TF. I missed my minus sign, so I got to keep this minus sign here. Minus 30.0 TF minus 600. Okay, and so then we can, let's add 30 to both sides. So I got 50 TF is equal to, let's add 1600 to both sides, so that's 1000. And so my TF, final temperature, is 1000 divided by 50. That's not right. Hold on, what did I do wrong? So added 30 to both sides, go to 50, and then add 60. Oh, I see the problem. This is plus 1600. Minus goes to plus. So 1600 plus 600 would be 2200. So 2200 divided by 50 is 44 degrees C. So our TF is 44. All right, this question here is looking at us, once it's defined the delta H for this reaction, so we just do the sum of the products minus the sum of the reactants. So what we're going to do here is do minus 1284.4 plus 5 times negative 167.1 minus negative 443.5, and then minus 4 times negative 285.8. So I get minus 533.2. And so we have to make sure that we take these two added together, this times 5 for the 5 moles, and then minus the sum of these two here. So the sum of the products minus the sum of the reactants. Question 9, which atom below has an oxidation number of plus 3? So minus 2, minus 4 for the 2, minus 1 overall has to go plus 3. So it's going to be actually the first one is plus 3. And then the second one, minus 2 is minus 8. To go to minus 3 overall would be plus 5. S2O3 to minus 2 goes to minus 6. To go to an overall charge of minus 2, then we have to have a plus 4 for the 2 S's. So this is a plus, not plus 3, plus 2. So plus 4 for the 2 sulfurs. So dividing this by 2 goes to plus 2. And then NO2 plus goes minus 2, minus 4. To get plus 1, we have to go 5. So 5 minus 4 is plus 1. So plus 5 for nitrogen and NO2 plus. Well, quantum numbers N of 4, L of 1, M sub L of 0 could represent a valence electron in which ground state atom? Okay, this is a 4p electron. Well, it's an electron in a 4p subshell. That's the right nomenclature. And so the question is, which of these atoms here has a valence electron in a 4p subshell? And so iron doesn't, because it's a, argon 4s2 3d6, so nothing into the p subshell yet. Indium is the next row down, so indium is a krypton 5s2 4d10 5p. It's right below gallium in the boron group 5p1. And so it has an electron in a 4p subshell. It's just not a valence electron. So part of the krypton configuration uses the 4p subshell, but not in a valence shell orbital. So no valence electron does in indium. I don't know why it's circled, but that's not the answer. Palladium, likewise, is also in the 5th row. I don't know why I'm circling this. It's not the right answer. So palladium's wrong because it's a krypton 5s2 and then 4d less than 10. So it doesn't have any electrons, any valence electrons in the 4p subshell. And then hopefully the answer is selenium, because it's all that I have left. But selenium would be an argon 4s2, 3d10, and then a 4p4. So it has 4 electrons in a 4p subshell. So the valence electrons in selenium could have a valence electron with that set of quantum numbers. Which atom has the largest atomic radius? So atomic radius is increasing down, and then, I don't know why I would write it that way, that doesn't make any sense. So it's increasing this way. Because we decrease size left to right, and then top to bottom increases. Increases, I wrote decreasing. So top to bottom size increases, left to right size decreases. So the largest atom is the one furthest to the left and down. And so let's reconstruct our periodic table. So SCl, selenium, bromide. And so this is going to be our biggest. So our size decreases to bromide. Bromine is smaller than selenium. Chlorine smaller than bromine. Sulfur's smaller. So these are definitely smaller. Chlorine is smaller than sulfur. Selenium bigger than bromine. So selenium is the biggest one of these four. Of the listed elements, which one has the highest first IE? So ionization energy increases left to right and decreases top to bottom. Okay, so I got lithium. Beryllium is next door to lithium. Sodium, magnesium. And so for the first ionization energy, magnesium is higher, but beryllium is higher because it's higher up. Beryllium is higher than lithium, and then lithium is higher than sodium. And so these, the lowest would be sodium, and then the highest is going to be beryllium. Okay. 13, which species is sp2 hybridized? Probably this one, but let's make sure we see why. So this is going to be linear. So BeF2 only has 2 for beryllium. So 2 plus 14 is 16. So we're good with this being sp. CO2, C double bond O, this is sp as well. Krypton fluoride is not going to be sp hybridized. This is going to be like xenon fluoride. This is going to be 8 plus 14, 22 electrons. So that's krypton, fluorine, fluorine, like beryllium, but one difference being 1, 2, 3 lone pairs. And this goes linear. I don't think we'd call it SP. The hybridization just is not SP2 is probably the best thing. So not SP2, that's SP, that's SP. We don't talk too much about the hybridization sets of the 5 and 6 coordinate atoms. But SO2 has 18 valence electrons, 6 times 3. So we have a central sulfur, oxygen, oxygen, lone pairs on the O's if we're following our basic construction of our Lewis structure. That's 16 electrons. The 2 left over go on to sulfur, and boom, this is our 2 domains. Now, of course, we're going to go double and then resonate over to the other side. So we're going to have this like 3 halves bond order, equal bond lengths, but still 3 total domains either way. So sp2 for this sulfur because it's trigonal. Which dot structure is best for SO3 2 minus? On a question like this, just sketch the Lewis structure. Just do the 6 plus 3 times 6 plus 2 for 26 total electrons, and then you'll get it right. Well, hopefully, every time. Single bond the O's. This is how we see that that's only 24 electrons, that the 2 left over go on to sulfur. We're going to miss those electron pairs every time if we're not counting single bonding starting from there. Now, we still have a positive charge. We can make a double bond, go to this. That's fine. That's going to satisfy the formal charge rule. Or so this Lewis structure is one of the 3 possible Lewis structures that minimizes the formal charges. Or we go with the S with 3 singles and a lone pair. Okay, so let's take a look for a minute here. This is good. This is almost good. Like A is almost good. So I'm looking at it. A is not good. Why am I circling answers that are wrong? Because we're missing the lone pair on sulfur. So this here only has 24 electrons shown, so that's why this is wrong. This here, likewise, we need a lone pair on sulfur, so C is wrong. And then D is wrong because notice that the oxygen still has, it didn't like lose the electron pair. So if I'm counting electrons in, let me do it with red. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28 electrons, not 26 that we should have. So that's why this structure is wrong. Okay, and so then we're going with answer D is the best one of the choices. And then we could have like had this as a choice too with the formal charge rule. Notice that the question didn't tell us which one is the best, but it does ask which one is a valid representation, not necessarily the best. So D is a valid representation, so 2 would be our formal charge rule structure, but none of the other choices in A, B, or C are correct. Question 15, manganese, what's the right count here? So for manganese, 2 plus, we've lost 2 electrons. Manganese is, I don't know why they don't just tell us the atomic number. Manganese is atomic number 25, just looking at a periodic table. So it's 25 protons, and then 2 fewer of that electrons, so 23 electrons. It doesn't help us. And then the neutron count is our mass number, is the sum of the protons and the neutrons. So we just subtract our 25 protons off, we get 30 neutrons. So A would be our right answer. The energy required to break 1 mole of hydrogen-hydrogen bonds is 436 kJs per mole. What is the longest wavelength of light sufficient to break this bond? And so this is where we use E is equal to h nu. This is per photon. So 1 photon interacts with 1 atom. So we want to say, well, what's the energy for 1 H2 bond instead of per mole? So for 1 H2 in joules, this would look like 436 kJs per mole times 6.022, sorry, wrong way, 1 mole of H2 is 6.022 times 10 to the 23 H2 molecules. We know the energy in 1 H2 molecule, so we're going to multiply by 1 H2 molecule to cancel here, and then just 1,000 joules, doing it wrong again. So a kJ on the denominator, so 1 kJ is 1,000 joules. So I'm taking 436, a little jumbled on the page, but 436 dividing by Avogadro's number, that would say, if we hit enter, that it's 7.24 times 10 to the minus 22 kJs, and then times 1,000 is 7.24 times 10 to the minus 19 joules, is the energy it takes to break the bond in 1 H2 molecule. So that's the bond strength of 1 H2 molecule in joules, and then we connect this to say, well, if our photon contains that much energy or greater, then it can break the bond. And so then the E is equal to h nu. We set the 7.24. Let's do our nu, or let's also relate h E is equal to h nu to hc divided by lambda, because lambda is what we want to solve for. We don't need the frequency, we want the wavelength. And so the wavelength is going to be the energy divided into hc. So we take 6.626 times 10 to the minus 34 joules times seconds times the speed of light, 2.998 times 10 to the 8 meters per second. Then we divide by the energy in joules, 7.24 times 10 to the minus 19 joules. And then we have to convert to nanometers. We're going to originally be in meters, from meters per second. And so if I do 6.626 times 10 to the minus 34, screwing my calculator up, 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8, and then divide by the answer previously. That gives me 2.74 times 10 to the minus 7. And then 1 meter, 10 to the 9 nanometers, so times 1 E9, 274 nanometers. So 274 nanometers contains the proper energy bond, and then in 17, Well, actually, there's two more questions. In 17, which change in principal quantum number for an electron in the H atom represents an emission with the longest wavelength photon? So the longer wavelength, so E is equal to hc divided by lambda. The longer the wavelength, the lower the energy. And so the lower energy um, emission comes from high to low, not low to high. So we need a high to low, and then 5 to 2 is going to be lower in energy than 4 to 1. So when we're thinking of our energy difference, or 1 to 2 to 3 to 4 to 5, so 1, 2, 3, 4, 5, our 5 to 2 difference is going to be a lot greater in energy than our 4 to 1. So the 1 to 2 is a huge difference of energy, 4 to 1 much bigger. And so our lower difference of energy is 5 to 2.